Hello, calculus. We're into derivatives now for chapter 2. We're not doing 2.1 and 2.2. Those are the limit definitions. We can skip over that as long as we remember one thing about it. The one thing you should remember from last year, it's a derivative finds rates of change. You might have used a different word, but a derivative finds slopes is what we're looking at. Rate of change on a graph is slope. We'll expand that kind of definition as we go through this chapter. But for right now, we're going to review those rules that you got last year. So, finding slopes. Remember, finding a slope at any point on an equation because curves change slopes. So that's what a derivative will do. All right, so we're not doing the limit definition. We're just going right into the rules, and we start with our power rule. And here is a big function definition. So what do we do with that function definition right in here? So remember your power rule. You should remember how to do simple ideas of x to the n power, n times x to the n minus 1. Think about what that means. That is this n down here. We would multiply by the exponent, so bring the exponent out front, and then subtract 1. So multiply it out front, subtract 1 is what we did. If we gave a real quick thing, if I told you y equals 7x squared, then our derivative, remember the notation here, here's our notation with a derivative of something. So with y, it would be dy dx, the derivative of y compared to x, that's our slope, change in y over change in x, is, let's see, multiply out front, so 14, 2 times 7, and then subtract 1, x, 2 minus 1 is 1. 14x is our derivative. Real quick and easy with any exponent. Now, we kind of just say power rule for all of these others. Coefficient, sum, constant. I just did the coefficient, really. We had a coefficient in front of something. A times a function, it was just a times the derivative. Really up here, x squared, the derivative would be 2x. And then we kept the 7, and we said 7 times that 2x. We just kept the coefficient in front. That's how we got our 14x. Sum just means when we add pieces together, we can do their derivatives separately. That's how we're going to do any polynomial. Okay? Anything added, and just do each one as separate power rules. And the derivative of a constant is 0. Okay, the derivative of 7 is 0. The derivative of 8 is 0. So any constant has 0 x's. 0 means it will not be changing. Okay, so there's 0 slope on a horizontal line. That's what that is. So constants, no variables. The derivative of that piece is 0. So remember our power rule. Multiply the exponent out front and subtract 1 from that exponent. Works for any exponent, positive, negative, fractions, whatever it is, as long as it's written as an exponent. So let's find these derivatives. I didn't do a lot of just basic simple ones. You know how to do that. We need to first make it look like a power rule. So first, write as variables with exponents. Okay, separate terms with exponents. We do not want any variables in the denominator. We don't want anything in radicals. Those can all be written as exponents, fractions and negative exponents. So with this one, I don't have separate terms. We're going to multiply this out. Now we have to remember how to multiply things out. So how do we do 2x times root x? Well, that root x is x to the 1/2. And you add exponents together, 1 plus 1/2. So this is 2x to the 3/2 minus, now we got to do 2x times 3 over x to the 4th. That x to the 4th is x to the negative 4th. Remember, any fraction, write as a negative, and now multiply. 6x, and when you add together, you get negative 3. That is not the derivative. We just had to make it look like we could do a derivative. Separate terms with exponents. So I didn't label as dy dx or anything. Always label derivatives. Know when you have done that. That is part of your answer. So y, when I do the derivative, becomes dy dx. We're going to use that notation. Remember, y prime is okay. It's easy to lose that prime, and we want to get this dy dx as a slope idea, change in y over change in x. So dy dx is multiply to the front. 3/2 times 2 is 3, and subtract 1. 3/2 minus 1 is 1/2. Be able to subtract fractions real quick. Next one, multiply the negative 3 out front, we get plus 18. Make sure you multiply that negative. Plus 18 and subtract 1. Negative 3 minus 1 is negative 4. We're done. You can leave your answer like this too. So you could say, or you could have dy dx, and you could put it back in the original form. It really depends on what you're going to do with this next. Okay, how do you want to use the derivative? 3x to 1/2, you could write 3 root x. You could write plus 18 and have that over x the fourth. Either one is fine for an answer. You should be able to recognize as you're checking your answers, either way it's written in the answer, you can have the other one and it would be true. Okay, you could have a correct answer that way. So if you're going to plug another number in next, maybe the second one is better. You at least have to understand that to plug the number in. But you can keep these with fractions and negatives. All right, number 2. So same thing. We have x to the 3/5. The second one is not written as a term with an exponent. So this one, instead of over root x, we're going to write x. Over means negative exponent. Root means 1/2. So that means the same as 2x to the negative 1/2. And now we can do our derivative. G gives us that notation, g prime of x. So with function notation, that's the function notation derivative, that prime, is, let's see, multiply in front, so 3/5, x to the 3/5 minus 1. 3/5 minus 5/5 is negative 2/5. Be able to do that quickly in your head. Now the next one, multiply by negative 1/2 in front. That changes to plus 1, 2 times 1/2, x, and subtract negative 3/2. That's fine for your answer again. You don't have to have that 1 in there. You could write it back into fractions, but you don't need to. Or into radicals, but we have a fraction in the original. So this is good enough for the answer. All right, next one. It looks like we have separate terms in the numerator, but we have this big fraction. Everything has to be separate terms. So we'll go over quotient rule later on another worksheet. But this one, we can divide by a single term. That's what we want to do. So remember, division is like multiplication. You can distribute division. Okay, that means the x to the fourth is divided by x squared. The minus 3x is divided by x squared. The plus 2x is divided by x squared. And the 1 is divided by x squared. And that makes x squared minus 3. Those are easy so far. 2x over x squared is 2 over x, or 2x to the negative 1. That's the better way to write this. And 1 over x squared is x to the negative 2. So get it written as separate terms. This is not a derivative yet. So make sure you do the derivative. All right, so now it's separate terms. And we can say, let's see, derivative notation, dy dx on this one. So use that notation, know when you've done a derivative. And we can go through these pretty quickly. 2x for the first one. 3 becomes 0, so minus 0. You don't even need to write that. Next one is going to be minus 2, and x to the negative 2. Make sure you subtract 1 correctly with negatives. And then minus 2, x to the negative 3. Multiply in front, subtract 1. All right. Don't write the minus 0 in there, and this is fine for your answer. So 2x minus 2x to the negative 2 minus 2x to the negative 3. Okay, depending on what we do next, you might factor it, you might write them as fractions, but you can just leave that right now as our derivative. Okay. All right, what about some trig functions? We aren't going to do all of them today, just these real simple ones. Hopefully you remember from last year. The derivative, ddx, of sine of x is, these were simple because sine and cosine are related this way. Sine of x derivative is just cosine x. We're not going to do the whole proof. You could look at the graph. There's other things, but we just need to know that sine of x derivative is cosine x. Okay. Cosine derivative of cosine, is not just sine x, though. That was negative sine x, has the negative in front. We're going to see patterns when we look at all trig functions later as we go through this chapter. We'll kind of get all of them and remind all of those. Trig function derivatives are ones we want to memorize. And this is all for the first day. Sine gives us cosine. Cosine gives us negative sine. So we can apply that down here, number 4. Remember this this thing here, this 0 with a line through it, that is theta. So theta is your variable. Oftentimes we use Greek letters for angles. And since we're using trig, we put that Greek letter in here. But you can do the same rules with any variable. So dy dx, not dy dx anymore, dy d theta is what this would be. There's our variable down there. So whatever variable is inside your problem, that's the one you're going to use in this notation. So the x is replaced with theta. Okay. Dy d theta is, well, this 3 theta, it's just 3 like 3x. That's just 3. Okay, theta to the first. So it goes 3 theta to the 0. It's gone. 3 minus, remember coefficient stays there, 4, and the derivative of sine theta is cosine theta. That's all it is. So the coefficient just stays there. The derivative of sine is cosine. So that's 3 minus 4 cosine theta. That's what we're going to use these with. Okay. So sine turns to cosine. Cosine turns to negative sine. You got to remember those. All right, keep going with it. Find the slope of the tangent. Some kind of word problems here. Find the slope means slope is from the derivative, means we are going to plug into, so we can find the number for the slope, plug into the derivative. Whatever they give us to plug in, and they have given us a point over here at 2, 3. So we're going to plug that in for x and y in our derivative. So find the slope of the tangent line. Or the idea is we've got this curve. Okay. If I want to find the slope right there, it's the slope of the tangent line, which touches it once. That's the direction it's going to go. Okay. So the slope of this tangent line defines the slope of the curve. All right. So that means plug into the derivative. We need to find the derivative. So first of all, I don't like the x the third on the bottom. I'm going to write that as x the negative 3. So dy dx is my slope is 2 plus, and now we have 24, negative 8 times negative 3 plus 24, x to the negative 4. Make sure you subtract 1 correctly. Okay. Now, at the point 2, 3, we've got to know how to do this. Now, notice we have an x variable. There's no y variable, so we don't even need that 3. In this case, we only need the 2. Let's plug it in. So this is 2 plus. Now, this is where you have to know what to do with the x to the negative 4th. The x to the negative 4th, you could write in the denominator, but the 24 stays in the numerator. So that will help you plug this in. You have to know what those exponents mean. So at this 2, we get 2 plus 24 over 2 to the 4th. That's 2 plus 24 sixteenths. That reduces to 3 halves. So 2 plus 3 halves, that's 4 halves plus 3 halves is 7 halves. The slope of the tangent line at 2, 3 for that graph is 7 halves. Okay. Number 6, another word here, find the equation of the tangent line. Anytime we're given an equation of a line, best way is point slope form. Y minus y1 equals slope times x minus x1. Okay, well, what do we need for point slope form? Almost the easiest question all year. We need a point to do point slope form. And we need a slope to do point slope form. So a point, we need an x, y. This is from the original function. Remember, a y equals function, an original function. If you plug in x, you get y. You get points on the graph. So the original function, plug in, we have x equals pi over 6. So Y is 2 sine of pi over 6. Sine of pi over 6 is 1/2 times 2, and that is 1. We just got the point, pi over 6 for x, 1 for y. There's our point. That's our x1 and y1 in the equation. And the slope, we use the derivative and plug in. So we need to do the derivative. dy dx is 2 sine x up here is what we have. So keep the 2, sine becomes cosine of x. So at pi over 6 again, you can't leave an x in here. You have to have a number for the slope. Plug into the derivative. So this becomes 2 cosine pi over 6. Well, cosine pi over 6 is root 3 over 2 times 2, and we end up with root 3. There's our slope. So point slope form, y minus our y value is 1 equals slope, that's root 3. And then x minus our x value was pi over 6. There is the equation of our line, tangent line to that graph. Okay, point and slope. Next one, find the equation of the normal line. Same information, same equation, same graph. We don't have to do anything extra. We just have to understand and remember what this means. A normal line means perpendicular to. So instead of our graph, here's our tangent line right there. At a point, our normal line is going to go straight through and be perpendicular. That's the normal line. Same point, perpendicular was the opposite reciprocal slope. So we have the same point. Our point on this one from the last problem was pi over 6 comma 1. Our slope, we had a slope of root 3. So now we're going to have negative 1 over root 3. And now we can write this again. Y minus 1 equals, this is the only thing that changes, negative 1 over root 3 and x minus pi over 6. So a normal line is perpendicular. All you have to do is change the slope. All right, number 8, last one here. Find all points where the tangent line is horizontal. So points, first of all, we have to give x and y. Find all these points along this curve. Tangent line is horizontal. Let's think about what that means. If we have a graph where we want the tangent line to be horizontal, we have to have something like this. Okay, there's a graph. And right there, the tangent line is horizontal. Okay. Anywhere else, it has a slope to it. Well, this one, remember, slope of a horizontal line equals 0. So that's our plan. Horizontal tells you get the slope to be 0, set it equal to 0. And the slope is our derivative. So we're going to do the derivative equal to 0 and find where that is. So the tangent line is horizontal where the slope, or dy dx, equals 0. So we need to find dy dx. This one, multiply the 3, you get 1x squared minus just a 4. And we want that to be equal to 0. That's what it means to find where it's horizontal. Well, this one's just x squared equals 4, so x equals, don't forget, plus and minus 2. You could factor that to get the plus and minus 2 as well. So we want points. So one is at 2 comma something, another one at negative 2 comma something. Remember, to find the y value of a point, go to the original function. So we're going to plug 2 in and get 1/3 times 2 cubed minus 4 times 2. That is 8/3 minus 8. 8's 24/3. That is negative 16/3. And if you do that for the other one, 1/3, and this is negative 2 cubed minus 4 times negative 2, you end up with negative 8/3 and plus 8. And that one is positive 16/3. Those are the 2 points where this tangent line is horizontal. Okay, this cubic graph does this, goes up, then down, then up. There's one there, there's one there. Okay, there's 2 of them where the tangent is horizontal. That's what we just found. So slope is 0, set the derivative equal to 0. All the little algebra solving in here we should be good with. just interpreting these words. All right, that's a quick review on power rule and a couple sine and cosine from the trig stuff. All right, those all should be pretty quick questions. These you're just plugging in at the end to find values. All the others, quick power rules, write them as exponents first. And that goes along with worksheet 2.3, or I call this the A section of the chapter, the first half. 2A3 is the worksheet for this one. All right, next is 2.4. We'll go over product and quotient rule. That's next up in the videos. Enjoy that one next. See you.